Welcome back to our Java Collections Mastery Series. Today we are tackling one of the most critical decisions in concurrent Java programming, that is choosing the right map implementation. We'll compare four essential map types: HashMap, Hashtable, ConcurrentHashMap, and synchronized map. Understanding their differences is crucial for building applications that are not only thread safe but also performant and scalable. Let's begin our journey into the world of Java maps. Let's start with HashMap, the workhorse of Java map implementations. HashMap provides a hash table implementation that offers fast key value storage with no thread safety guarantees. It designed specifically for single threaded applications where maximum performance is absolutely essential. You will find HashMap used everywhere, from simple caches and configuration storage to temporary data aggregation and any scenario requiring fast key value lookups. Now let's look under the hood at how HashMap works. Internally, HashMap uses an array of buckets that starts with 16 elements by default. When collision occurs, meaning multiple keys hash to the same bucket, HashMap handles them using linked list. In Java 8 and later, when a bucket becomes too crowded, it converts a linked list into a red black tree to maintain performance. This smart design choice keeps operations fast even with many collisions. The load factor, set to 0.75 by default, determines when array should resize to maintain efficiency. In this video, we are focusing on thread safety aspect of the maps. So if you need deep dive session on internals of map, drop me a comment down below. Now let's examine HashMap's iteration characteristics. HashMap implements fail fast iteration semantics. This means that if you modify the map structurally during iteration, the iterator will immediately throw a concurrent modification exception. This behavior serves as an early warning system, preventing you from continuing with potentially corrupted data. However, this also means HashMap is completely unsuitable for concurrent modification without external synchronization. In fact, concurrent modification in older Java versions could even cause infinite loops. Let's see HashMap in action. Here is the typical HashMap usage in single-threaded context. We create a HashMap, add some key value pairs, and iterate through them safely since we are in single-threaded environment. Now let's move to the HashMap's synchronized predecessor, Hashtable. Hashtable represents Java's original thread-safe map implementation dating back to Java 1.0. While largely superseded by more modern alternatives, Hashtable still appears in legacy code bases where simple thread safety is needed without optimization for performance. It shares the basic hash table structure with HashMap but takes a fundamentally different approach to thread safety that comes with significant cost. Let's examine Hashtable's thread safety model. Hashtable achieves thread safety through fully synchronized methods, meaning every single operation acquires a lock on the entire hashtable instance. While this approach provides thread safety, it creates substantial performance overhead in multi-thread scenarios. Every get, put, contains, and remove operation must wait for the lock, leading to high contention when multiple threads access the map simultaneously. Here is how you can use Hashtable in practice. Hashtable usage looks similar to HashMap but with built-in synchronization. However, there is a critical detail often overlooked. Even with Hashtable's synchronized methods, iteration still requires external synchronization to be fully thread safe, when other threads might modify the map during iteration. Now let's explore a more flexible approach to thread safety. Synchronized map. Collections.synchronizedMap provides a wrapper that adds synchronization to any map implementation. This approach offers great flexibility than Hashtable because you can add thread safety to existing map implementations like HashMap, linked HashMap, or tree map. The wrapper works by synchronizing every method call on a mutex object, providing thread safety at the method level while preserving the underlying map's characteristics. However, this flexibility comes with responsibilities. Like Hashtable, synchronized map exhibit fail-fast iteration behavior and requires explicit client-side synchronization during iteration. You must manually synchronize on the returned map during iteration to prevent concurrent modification exception and ensure thread safety traversal. This design places more responsibility on the developer but offers greater control over synchronization. Let's look at a synchronized map example. With synchronized map, we must explicitly synchronize during iteration. The synchronized block ensures no other thread modifies the map while we iterate. This pattern is essential for thread safe iteration with both hashtable and synchronized map. Now let's examine the modern high performance alternative, concurrent hash map. Concurrent hash map represents a sophisticated high performance concurrent map introduced in Java 5 and significantly improved in Java 8. It's designed specifically for high throughput concurrent access in modern multi-core system. Unlike Hashtable's coarse-grained locking, concurrent hashmap uses fine-grained synchronization strategies that minimize contention while maintaining thread safety. Let's explore concurrent hashmap's internal architecture. In Java 7 and earlier, concurrent hashmap used segmentation strategy, dividing a map into multiple segments that could be locked independently. Java 8 improved this design by using an array of buckets with fine grained locking or even lock free operations for read. For write, it uses synchronized blocks at a bucket level or compare and swap operations dramatically reducing contention compared to Hashtable. Compare and swap CAS is a fundamental non-blocking atomic operation used in Java for concurrent programming. It updates a shared variable only if the variable's current value matches an expected value, thereby ensuring thread safety without explicit lock. We'll revisit this concept when we discuss atomic classes in future videos. Let's now examine concurrent hash maps iteration model. Concurrent hash map features weakly consistent iterators, which is fundamentally different from the failed fast iterators of HashMap, Hashtable, and synchronized map. Weakly consistent iterators reflect the state of map at some point since the iterator's creation. They may or may not show updates made during iteration, but they will never throw concurrent modification exception. This allows safe iteration without synchronization. Here is concurrent hash map in action. Concurrent hash map simplifies thread safe operations. Here, iteration requires no external synchronization because iterators work on a snapshot or weakly consistent view. This makes it ideal for scenarios where you need to iterate while other threads may be modifying the map. For concurrent scenarios, concurrent hash map offers elegant solutions. Concurrent hash map enables truly concurrent modification patterns. In this example, thread 1 iterates through the map while thread 2 modifies it concurrently. Because concurrent hash map uses weakly consistent iterators, thread 1 continues iterating while thread two's modifications may or may not appear in the current iteration but will never cause exceptions. Concurrent hash map offers powerful atomic operations. One of the concurrent hash map's most powerful features. These methods allow you to perform complex operations thread safely without external synchronization. The compute if absent, compute if present, and merge methods provide elegant solutions to common concurrent programming challenges. Let's see these atomic operations in practice. Here we use concurrent hash maps atomic operation to implement a thread safe cache with lazy initialization. The compute if absent ensures that expensive computations happen only once per key, even when multiple threads request the same key simultaneously. Here are the methods that allow more complex compound actions to be executed atomically using lambda expression. We saw compute if absent. If the specified key is not already associated with a value, it attempts to compute its value using the given mapping function. Compute if present. If the value for specified key is present, it attempts to compute a new mapping given the key and its current value. And last, put if absent. If the specified key is not already associated with a value or is mapped to null, it associates it with given value. Now let's examine a common pitfall with synchronized map. This example shows a typical mistake developers make with synchronized collection. The developer assumes that because individual operations are synchronized, compound operations are also thread safe. However, between contains key check and get operation, another thread could modify the map leading to rest conditions. That's why we need to put all these compound actions in synchronized block to make it thread safe. Now let's discuss critical best practices. First, never modify a map directly while iterating over it, except through the iterator's own remove method or concurrent hash maps atomic operations. Second, always synchronize the entire iteration block when using synchronized collections. Individual method synchronization doesn't protect iteration sequence. And third, prefer concurrent hash map over synchronized wrappers for high concurrency scenarios because it offers better scalability and performance. Let's quickly consider memory visibility in concurrent applications. When sharing maps between threads, you must consider memory visibility. Simply declaring a map as a field doesn't guarantee that changes made by one thread will be visible to other threads. For proper publication, use final fields, volatile references, or concurrent collections that handle memory visibility internally. There are some alternatives as well, which can be considered as per requirements. For example, linked hash map, which maintains insertion or access order with predictable iteration. Tree map, which supports sorted keys with OOP login operations. Concurrent skip list map, which is concurrent sorted map with again OOP login operations. Immutable map by Guava library, which provides truly immutable map for shared read-only data. And weak hash map. Here entries automatically removed when keys are garbage collected. And finally, let's review key takeaways. Each map implementation serves specific needs in the Java ecosystem. HashMap provides maximum performance for single threaded access. Hashtable offers simple thread safety for legacy scenario. Synchronized map adds thread safety to existing map with client managed iteration synchronization, and concurrent hash map delivers high performance concurrent access for modern applications. The right choice depends on your specific requirements for thread safety, performance, and iteration behavior. So, I would like to remind you this: always match the implementation to your actual usage patterns and concurrency requirements rather than defaulting to familiar choices. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.